I'll be talking about high-speed optical recording with a sub-picosecond rolling camera shutter. I am Ryan Muir, and I invented this with John Heebner. So here at Lawrence Livermore National Laboratory, we have the National Ignition Facility, where we focus a large number of lasers down to a single spot, that is to a single target, and that target explodes with science, and it's our job to figure out both what went into and what came out of that target. All of these lasers going in are extremely fast events, very fast pulses that we have to determine what they look like in time. We don't have the luxury of being able to signal average across hundreds, thousands, or millions of times to get a good signal. We have to look at this single event and get high quality information about it the first time and every time. So the question is, how can we measure these high-speed single events? And there's actually several different areas that have the same problem. In the world of lasers, besides us, there's just general research on petawatt lasers and rogue waves and high energy density science. In the world of biology and chemistry, there's work on scattering dynamics imaging and fluorescence lifetime imaging that can go down to picosecond or single picosecond time scales. In the world of telecom, there's characterization of time division multiplexing systems. In the world of optical shaping, there's optical arbitrary waveform validation and pulse compression and stability validation. And there's even applications in the world of semiconductors. So the current theoretical limits of single-shot recorders, the fastest available are oscilloscopes. With oscilloscopes, the fastest that's been demonstrated so far is a 7.8 picosecond resolution. If you want to go even faster, you can go to a streak camera. And streak cameras have been invented that go down to resolutions of a staggering 180 femtoseconds. But truly, if you want to get a practical resolution out of this, you have to go to about greater than a picosecond at least. When you venture down shorter than about a picosecond, the fidelity becomes very poor and the quality of your information is just not usable. And with oscilloscopes, looking towards the future, it was predicted by Walden that a purely electronic oscilloscope would not have even a single bit worth of information fidelity when it comes to signals faster than about a picosecond. Therefore, for a single shot, an oscilloscope would not be able to resolve what happened. Instead, with our technology, what we do is instead of transcoding this information from the optical domain to the electronic domain for processing, we leave everything in the optical domain. We process and chop and shutter in the optical domain, which maintains our high resolution and high fidelity. So the limits of this technique are not necessarily bound by the same constraints as electronic techniques. And indeed, this technique can go shorter than even 0.1 picoseconds, mainly limited by available laser technology. So the way that this semiconductor-based approach works is that it is actually very similar to a rolling camera shutter for those that are familiar with digital photography. So we have a semiconductor surrounded by supporting optics, shown here in this particular graphic. And when the semiconductor has a pulse of light shine upon it, the shutter effectively opens, allowing light through to the camera. But when there's no light present, no light gets through to the camera, of course. If we shine a very short pulse of light onto it, perhaps, for example, from a picosecond laser, the shutter is opened for effectively 1 picosecond. And finally, if we shine that light on it at an oblique angle, it races across the surface and we get a rolling shutter. This effectively maps time to space as our optical pulse, I should say, hits this side first and runs all the way and hits this side last. So in this demonstration we have a double pulse of light that would transmit through the system that's shuttered by our green pulse, and what a double pulse in time is turned into a double pulse in space. Therefore, the double pulse in time is recorded by the camera in space, and we get time to space mapping. This is called slanted light interrogation for cross-correlated encoded recording. We have a demonstration of this setup here. We took that double pulse in that previous slide and we recorded it with an oscilloscope. This is a fast oscilloscope, a 45 gigahertz Teledyne LaCroix oscilloscope, and we can see that the two pulses were about 50 picoseconds apart with a resolution of about 20 picoseconds. With our technology, we got 50 times the resolution. And we could see that precisely they were 52 picoseconds apart. We've also put together a second demonstration of a long record, and in this case we had a record length of more than 600 picoseconds with a good resolution as well. In this case, this preliminary data set was not normalized or calibrated, but a calibration process would flatten out the entire record across all the way to ones. This technology can be modified to perform functions that are completely different from the original slicer technique. For example, this could be used to create a high-speed single image capture, rather like a framing camera. Or we could have a wavelength versus time capture, rather like an all-optical spectrograph, using the second dimension of information on the camera. We could have multiple recording channels, rather like an oscilloscope, or we could even have a one-dimensional image versus time. And finally, this technology is available for licensing. We can either co-develop this technology for these specific applications or potentially others. Thank you for your time. For more information, you can contact the Innovation and Partnerships Office.